Let's move on to distance and location. And for that, we have to really, I mean, if we want to do it right, we have to go back to the Greeks. Good old Greeks, they gave us this, head start. They said, hey, here's our starting point. You guys take over. And they did a lousy job. That's the reality. And such a lousy job that no one has corrected them in the last 5,000 years. We still have the notions that the Greeks had, and they did a lousy job to begin with, so we ended up with a lousy job today. Why? Because we ended up with mathematicians in charge of physics. Mathematics has no place in physics. Physics is explanation, mathematics is description. There should be no interference by mathematicians in physics. Physics that we do here with objects, not with equations. Even though I'm going to do a little bit of equations, show you that I have a tinge of mathematician in me. Okay, so let's start with the Greek schools here. And just to put it in the right context, here were some of the most famous Greek schools, right? Lasted couple hundred years at least, right? And we're going to look at one specific one, and that's the one on the far left there. These fellows here on the left, they were from Elea, and they were the Eleatics, okay? And who were the Eleatics? Well, let's go with what they really believed in. We have their Parmenides. I think he was the father of the Eleatics, essentially. He was the founder. Then you had Zeno and Melissus, but they all had this idea that there is no motion in the universe. Yeah. Were they serious? Yeah, I mean, I can move my hand. What do you mean there's no, I can see it moving. And so they had this notion, they arrived at the notion that there is no such thing as motion, no such concept. Motion doesn't exist, that's essentially it. And here's Zeno. Aristotle covered him, and so did Plato, but Zeno, we have no written stuff from Zeno. We have only paraphrasing by Aristotle and Plato, okay? And so here you have Zeno, and he's got these two famous paradoxes. And actually, he had several. He had like 19 paradoxes that have survived, but these are probably the two most important ones. The first one is the famous Achilles and tortoise. Tortoise has a head start, and in order for Achilles to catch up with the tortoise, he's got to cover half the distance first, and then half the distance from where the tortoise went afterwards, right? And then half the distance, so on. So they have all these infinite half distances, right? And so it turns out that according to Zeno, the Achilles never catches up with the tortoise, because mathematically, right? Because what happens is you always have to cover half the distance first. Okay, and what it is a play on distance and infinity, the fact that you can divide distance infinitely many times. This is where some of these infinities came into physics. They shouldn't have arrived there in physics at all. This is something related only to math, but they introduced it into physics. And what's the issue? Here you have Zeno, he explains it. He says the tortoise paradox, right? The competitors start running at the same time, and he says during this time the tortoise run 2 meters. It will take Achilles some further time to run that distance. Okay. In other words, he's explaining that as the tortoise moves, Achilles has to make up half the distance first. Okay, and so he never manages to catch up with the tortoise. And so essentially, this is a mathematical exercise that's got to do not with physics. It's got to do with something else. It's got to do with this, with lines. Okay, here we have the line. Okay, and what they're saying here is that a line is made of points. So you have a line segment, right? And we're going to chop it up into points. Well, how many points are in a line? Well, all mathematicians will tell you that there's infinite points, meaning there's infinite line segments within a line, okay? Because you can take any 2 points and draw a line. 2 points make a line, right? So since it's got infinite points between any 2 points, you always have a line segment. And because you always have line segments, right, you're going to have infinite segments. That's essentially what good old Zeno was saying. But what's the problem with this? The problem with this is that they're not talking about line segments. They're not talking about geometry. They're talking about itineraries. But see, they turn geometry into an itinerary discipline. It's got nothing to do with objects. It's got to do with how you unroll the measuring tape around an object, be it a cube or a ball or whatever. So what they're talking about really is lines and chopping up the line into segments. And that's why they say they have infinite segments. And that's the case of the distance. Now, on the bottom, you have the other guy, the guy who shoots the arrow. And Zeno was saying, the arrow doesn't move. You say, what do you mean the arrow doesn't move? It hit William Tell's son's apple. What do you mean it didn't move? So what happened just now? And so what they have there, this is now no longer on distance, but it's on time. It says time is made of moments or instants. Moment and an instant is equal to 0 time, right? Because like a cross section of time. And so they concluded that if it's 0 time, the arrow is really not moving because it's occupying 0 time to present. So where's the motion in the present? That was his rationale for this. So he concluded in both from the distance and from the arrow there, in both cases he concluded that there is no motion. No such thing as motion. Motion is an illusion. It's an optical illusion. There is no motion. And the only clarification I want to say up there is, you have the physics distance is just separation between the tortoise and Achilles, whereas the mathematical one is distance traveled. It's got nothing to do with the distance of physics, and that's where we find our biggest problem. Okay, and the Greeks never picked up on that because they were mathematicians. Plato said anyone who doesn't know geometry is not allowed to enter here. What was geometry? Math. It had nothing to do with things, with objects. What's a point? Point is 0-dimensional, right? That which has no part, Euclid said, right? So if that's which has no part, what kind of geometric figure is that? When he defined figure, same Euclid, as that which has boundaries. What kind of boundary does a 0-dimensional point have? And same with line. Line is 1-dimensional. What are the boundaries of a 1-dimensional whatever? So these are not geometric figures. The point is a location, and the line is an itinerary. So they're not talking about physics. They're talking about something else. Okay? They're talking about math, and they're going to describe with an equation the point and the line. That's what it was all about. And a fellow who came a few centuries later, his name was René Descartes, he came up with this. He wanted to know the position of a fly on the ceiling. I guess that's where he got his bright moment. And so he figured if he goes 4 steps to the right and 3 steps to the north, he arrives at where the fly is. So he came up with this Cartesian coordinate system. Okay, he published that in 1637, and this is what we use today. This is what everybody's being taught in high school, at least, right? If not in college. Okay, so these are known as Cartesian coordinates, and it allows us to locate things in space. They call it space. I don't know why they call it space. Space is not a thing. It's nothing. No, you have to locate it somewhere, and hopefully you locate it in a container of sorts, like inside a room or whatever. Okay, and then again, here's the let me skip this, otherwise we go too long. So how do we destroy all these notions? We got to get rid of Zeno and Descartes. We got to get rid of all of them because they're doing math, they're not doing physics. And so they got confused with all these notions. They said, look, we have distance, we can chop it into all these little segments. We're really talking about itineraries. Then the other one, you're talking about time. You say, well, it's made of moments of little segments of time, instants, right? And so the question is, what are they talking about? What are they talking about when they say a moment? What are you talking about when you say an instant? And we destroy it with the tool that I've invented. I recommend everybody use it. It's called the universal movie. Universal movie is every atom in the universe in a single frame. Okay, God takes a picture and you have every atom at a given location. Every atom has distance with respect to all other atoms, right? What is the location of one atom? It's a set of distances to all other atoms in the universe. Okay, very simple. And so in a single frame, all you can have is some of these static concepts such as object, distance, location, and existence. And you can see the word distance is up there. So what are these people talking about when they talk about distance? Well, they're referring to something else. They're referring to distance traveled, okay? And when they talk about time, they're also talking about something else. They're talking about moments. Here's distance traveled, okay, displacement. You can see it's on the opposite side of distance. The one on the bottom has to do with math, okay, and the one on the top has to do with physics. Distance is simply separation between objects, between atoms. Distance traveled, that's something the mathematicians do because they unroll the measuring tape and they want to know how far something is. So they're not talking about a fixed distance separation. They're talking about how much they have to unroll a measuring tape that has units that have been predefined. And that's in case of the distance. And again, here you have the one for time. You have moment, duration, and instant are at the bottom, together with time. They're on the far right. Okay? Why? Because you can chop up distance traveled. You can chop up moments. You can chop up instants, time as much as you want. You want to chop it infinitely many times? No problem. You will always end up with two frames for motion or for time. So this is where they failed. They failed because I can take, an instant. What is an instant? Instant requires two frames because it's time, and time is defined as at least two frames, right? You need two frames to conceptualize time or motion. So what these people never realized, they thought it was a cross section, but a cross section of time, a cross section of motion is called location. It's not called an instant. It's not called, a segment of distance, an itinerary, which is what Zeno was talking about. You can chop up as many times as you want. If you end up with either motion or time or any subcategory such as an instant or a moment, you have to have at least two frames. So I don't care how many times you chop up motion or time, you're always going to end up with two frames because the definition of motion and of time is two frames as a minimum. Okay, I hope we got that straight. On the other hand, separation, we can see separation in a single picture of the universal movie. We take a snapshot, there you have separation. So separation is different than distance traveled. Distance traveled is the one of math. So what's the problem? Well, you have, you say, is there a problem with this? Yeah, there is. Here you have good old Newton, who lived in the 16th and 17th century, right? And he came up with this. He came up with force equals mass times acceleration. And he came up with force equals mass divided by distance squared, which is the gravitational equation, right? So he's got these two relations, right? And one of the things that the mathematicians do today, they put one equal to the other. Like force equals mass times acceleration is equal to, and they start playing around with all these variables and constants and so on, right? We got a problem because these two are qualitatively different. They're not the same thing. The distance in the acceleration formula at the top, that's distance traveled. The distance in the one at the bottom, the distance squared, that's separation between two objects. Okay? Let me go over that in a second here, but here it is. We make a change to good old Newton, okay? We say this is what's happening, okay? We have, at the top we have force, but at the bottom we have something different, not force, but tension. What we have is a tug of war in a snapshot. We have weight, that's the W in the thing at the bottom there. You can see the little W's, that's weight. On the other hand, you have distance traveled in the top one, Okay, so we're talking about two different things. In the top, we have velocity, right, which is obviously something in motion, right? And at the bottom, you have weight, and weight is a static concept. You have weight for any location in the universe. Okay, so weight is a static concept. And here, let me illustrate that. Okay, here you have an astronaut. Okay, who's falling to Earth, and you can see how the ropes fan out. Okay, at different frames of the film, right? So we have 3 different frames, and you can see what's happening. The ropes are fanning out, but we freeze the frame. And for that astronaut, we can just look at it as a single atom in his body, right? So all these ropes from the Earth are converging upon a single atom in his body, right? At a given location, because it's a static concept, that's the weight of that atom at that distance from the Earth. So weight is a static concept. We can conceptualize weight in a single frame. We can conceptualize weight simply by the number of ropes, effective ropes that converge upon that atom. Okay, so yes, weight is a static concept. Okay, it's not a dynamic concept, and people have this notion that it's a force, and no, it's a tension. There you have the T for tension. Okay, so let's get it right. Newton had it wrong. Tension's not a force, by the way. A force means that someone does win the tug of war, whether you push or pull. Tension, everybody has a tied game. Nothing's moving. Tension is a static concept, and so is weight. Okay, so the distance in the bottom equation is not the little s, which is distance traveled in the upper equation. Okay, and another ridiculous thing that they have, and that's because it's math and not physics, is that they have velocity for a single point. Okay, they say at this point this was the velocity, and so that's the speed at that point. Except that speed doesn't have direction. Velocity has direction, but that's irrelevant here in a sense. First, because direction is a qualitative concept that belongs to physics. There is no such thing as direction in math. Okay? You're not going to put direction in an equation. What are you going to put, right? So what you have is velocity at a single point. But that's a problem because velocity is a segment. Velocity means something is moving. And so you say, well, how do they have velocity at a single point? I never understood that in high school. Then I figured it out. Yeah. What they're doing is cheating. They take the limit or whatever, and they say at that point you have such and such velocity, right? But see, velocity requires a segment. Okay? Velocity is motion. Motion requires 2 frames. You can't have a single frame for velocity. Math can get away with that, not physics. Okay, let's get that right. Okay, so this is part of the problem. Okay, so here we have the differences. We're going to compare distance versus distance traveled so you see the difference. Okay, here we have side by side. We have the force equals mass divided by distance squared, the gravitational formula on the left, and Newton's second law on the right. Okay, what are the differences? Distance is static in the one on the left. The other one is dynamic. Something is moving. You have an object that is moving. Okay, it's got velocity, right? That's the V. Okay, here you don't. You have static. You have a value of weight for a given location. So the distance is just separation. That's what that D in the denominator tells you. Distance is between 2 objects. The other one is the distance of one object traveling outwards. Okay, from a given point, a reference point. Could be the same object itself, its starting point. Okay, each frame in the movie depicts a static distance, whereas the other one is an itinerary. Okay, a cross section of an itinerary. That's what velocity is. Cross section of an itinerary. But again, if you have a cross section of motion, infinitely cut motion. I don't care how much you cut it. It's going to end up with 2 frames because motion requires 2 frames. The velocity is motion, you need 2 frames. And distance decreases. You can see distance decreasing as one object approaches the other one. In the other case, the distance is increasing, okay, because you're unrolling the measuring tape, okay? And here you're just checking the separation. You don't care about the numbers, you don't care the units, you don't care how much. You just say, hey, the distance, the separation is decreasing. So you don't need to know how much. The other case, you need to know how much because you're going to be calculating, how much this thing traveled or whatever, how much time it took, whatever you're trying to calculate, but you're unrolling the measuring tape so the distance is increasing. And then the distance is towards the object that you're moving, and the other one is away from the object. It could be, again, the same object starting point. So you can see that the distance in the force, mass times acceleration, is different than the one for the gravitational equation. Okay, so now what is it we're doing? Well, that's what we're doing. We're unrolling the measuring tape. Okay, that's what math is doing. And so that's not the same thing as a separation between the two hands there. Separation there is just, we don't care how much. We're just saying there's so much separation. Here, there's less separation here, here. And, the closer you get your hands, you get less separation. We don't need to have a value. But when they unroll the measuring tape, they're doing math and not physics, okay? Because we don't care how much or what units. Mother Nature surely doesn't know anything about meters, okay? Okay, and here you can see that velocity and so on. You have all these definitions for speed, for duration, for velocity. They're all dynamic concepts. Weight is interesting because they don't have a definition. They have no idea what weight is after so many hundreds of years, okay? Says there is some variation debate as to the exact definition. This is out of the Wikipedia, by the way. Some standard textbooks define weight as a vector quantity. Others define weight as a scalar quantity. Yet others define it as a magnitude of the reaction force exerted on a body. Okay, so they have all these definitions for weight, and all the others are dynamic. So here we are, so many centuries later, nobody knows what weight is. So when they say, what's your weight? You say, well, I don't know because I don't know what weight is. That's the answer. Okay, so here we have another issue which is troublesome, and keep this one in mind because it really is troublesome in physics, okay? And here it is that the fact that they equate this length with distance. Why? Because they're going to be measuring not distance, they're going to be measuring distance traveled, unrolling the measuring tape, the tip of the measuring tape. In the physical sciences and engineering, the word length is synonymous with distance. Absolutely. There's no difference in math between length and distance. Length is defined as straight line distance between 2 points. Length, the longest extent of anything as measured from end to end. And length is straight line segment, the distance between its endpoints. What they're doing is equating length with distance when these are qualitatively totally different in physics. In math, you can do whatever you want because all they're measuring is how many units. So they don't care if they measure length or measure distance. To them, it's the same because they're just going to give you a number, so many meters, so many yards or whatever, right? So they don't care what they're measuring. And for them, it's the same thing. And so, yeah, this is where we run into trouble because they're equating length with distance when they are qualitatively different. And here you have the definition from good old Wikipedia. It says length is a measure of what? Of distance. Absolutely not. Length is a quantity with dimension distance. With dimension distance? What the hell is the dimension known as distance? I never heard of it. I knew about length, width, and height, but now they have all this nonsense calling a dimension is a distance. So I don't know, you figure that out. It says length is commonly understood to mean the most extended dimension of a fixed object. No, I don't know if it's they're confusing measurement with the length, width, and height notion of length. Okay, so you can't confuse the two. There's two. They use the same word, and I think they get confused 90% of the time. Length meaning measurement of distance is different than length, width, and height, the length of physics. And this is what they're saying. It's the most extended dimension of a fixed object. No, length doesn't have any extension. Length, in other words, doesn't have any numbers. It's not the longest. All the length, width, and height are all of the same length because they're qualitative. We don't say, oh, the length here is longer than the width. No. Length, width, and height are just perpendicular straight lines. Right? Mutually perpendicular straight lines. That's all it is. So they have no length, neither one of them. None of them. Okay. Various terms for length of a fixed object are used, and these include height. Okay, but here comes the big shocker. Okay, it says or vertical extent, width, breadth, and depth. Breadth and depth are not dimensions, but these people don't know the difference. And one of the things you should be aware of is that like in Spanish or in German, right? Breadth and depth. Breadth, especially breadth, does not have, there's no word for breadth. And breadth is a vector. Breadth means that you're moving, means the movement in sideways direction. That's what breadth is. Okay, and they don't have a word for that in Spanish or in German. That's so funny. I found out that a long time ago, that they don't have a word for it. They do have depth, and they do have elevation, which is the other vector. But breadth, depth, and elevation are vectors. They're not dimensions. These people don't know the difference between a dimension, a vector, or a coordinate. Why? Because for them, they're all number lines. They're number lines. They're not vectors. They're not dimensions. They're not nothing that we do in physics. They're all number lines. They're looking at the values. And so you have these incongruent definitions or notions that these people hold today. They talk about breadth when they should be talking about width, not breadth. And there at the bottom, I summarize it. Distance is what lies between lengths. Okay, what is it? Distance is the separation between objects, whereas length is the continuous matter that you find within an object from surface to surface. And so let me show you that here. Here's the rational version of all these words. Okay, distance, separation between two objects. Okay, length, continuous matter within the boundaries of an object. Okay, length is to matter what distance is to space. Okay, what is space? Nothing. That's distance. Nothing. Hopefully, there's nothing there. Okay, even though under the rope model, the distance, ironically, is the length of the rope from atom to atom. I mean, if you're going to look at an object, you have a set of ropes, okay? But if you're looking at just two atoms, the distance between them is the length of the rope. That's so funny. But that's what it is. But then you have to put it in the right context, okay? Okay, and because of all this nonsense, we end up with this individual. His name is Albert Einstein, good old Einie. And Einie came up with more ridiculous stuff. He wasn't really the one who came up with it, but they attributed to him, so I put him in there as the poster boy, okay? So don't laugh at me. There it is. And he came up with length contraction. Actually, it was, other people. But what is it? You have that little equation right there in the square root, and you see the little v there. The little v is velocity. That means the velocity of the object. As it approaches the velocity of light, which is the c squared on the bottom, you get 1, right? The closer v squared is to c squared, the more you have this 1, value that's almost 1. And if you have 1 minus 1, you have 0. And so the square root is undefined. That means this value is undefined. And that's what led Einstein and who knows who else to say that, you can't travel at the speed of light because you turn into what? Energy, whatever that is. Okay, but this is what we're talking about here. They talk about length contraction, but they're talking about distance contraction, meaning distance traveled contraction. They call it length contraction, but they're going to be measuring with the tape. They're saying, look, the measurer, the observer, the guy who's measuring, right, is going to measure at v equals 0. He's going to measure the ball somewhat, whatever value he's got there. But as the guy travels close to the speed of light, the observer, right, not the guy in his proper frame, because that guy doesn't see any difference, but the guy from far away who's measuring that, he's going to measure a contraction. It's Einstein's tongue contraction. That's what I call it, And so you have this contraction of the ball, but did the ball actually contract? And no, because it's an optical illusion, it means that the guy's going to measure something different than what is reality. So the ball did not contract. What they're saying is because in the proper frame, the guy doesn't see any difference. It's the guy from far away who measures, right, distance traveled, and he's going to measure the distance traveled from one edge of the ball to the other. He's going to unroll his measuring tape and measure distance traveled. And they call that length contraction. You figure it out now. So yeah, this is the problem. Language, and more language. You have to get the language straight. And here we have a different language, yes, but we have a rational language. They say, oh, but everybody talks this other language. Yeah, because they're talking nonsense. They're talking irrationality. Okay, so back to what I said before here. Distance, separation between two objects. Length, continuous matter within the boundaries of an object. I think it's straightforward. Distance is what lies between length. Length is the matter. What distance is to space. If God wants to have distance, if he wants to have location, really, he has to have distance with respect to every object in the universe. And here we see him, once again, good old God. He's got to have distance to every object in the universe. Okay? Then he has location. And if he has location, guess what? He has existence by definition, because exist means object that has location. God right there has distance to every atom. I hope those lines represent that, right? And so good old God not only has location, he finally has existence. We finally made poor old God exist. So please believe in God, because he exists. There you see him. Very clear, right? Okay.